All right, today we're going to decode what looks like a pretty secret language, the pump performance curve. Now these charts, they can look really complex, but trust me, they're the key to picking the right pump, running it efficiently, and stopping it from, well, catastrophically failing. Let's get right into it. So imagine you're choosing a pump for a really critical system. How do you actually know it's going to work? I mean, choosing blindly is just a recipe for disaster. We're talking inefficiency, high costs, and maybe even total failure. But what if a pump could actually predict its own future? Well, it turns out it can. That performance curve isn't just some graph. It's the pump's secret roadmap. It literally charts out its entire operational life, showing you its power, its efficiency, and its absolute limits. And today, we're going to learn exactly how to read it. So this roadmap is created by the manufacturers through some really rigorous testing. What it does is it plots the pump's key characteristics against its flow rate, giving us a super reliable prediction of how it's going to perform out there in the real world. This roadmap plots a few key things. On the horizontal axis, you've got flow rate. That's just how much fluid is moving. And on the vertical axis, you've got head, which is basically its pushing power, or pressure. Then we layer three really crucial curves on top of that. One for efficiency, one for how much power it needs, and one that helps us avoid this really destructive thing called cavitation. Let's start with the most fundamental relationship on the chart, head versus flow. This curve answers a really simple question. For any given flow rate, how much pushing power or pressure can this pump actually generate? Think of it like a seesaw, because that's the perfect way to picture this core trade-off. The relationship is inverse. If you want high pressure, you have to accept low flow. If you want a ton of flow, well, you're going to have to accept lower pressure. You just can't have both at the same time. It's a constant balancing act. You know, the shape of this curve is also a dead giveaway about the pump's personality. A nice, stable, continuously drooping curve like this one, that's what you want. It means the pump is going to behave predictably. But a curve with a hump in it, oh man, that can lead to unstable operation, surging, and just all sorts of headaches down the line. Okay, on to the next critical element, efficiency. Knowing the pressure and flow is great, but this is where we start talking about the money. The efficiency curve tells you exactly where you need to operate the pump to get the most work done for the lowest possible energy cost. The very peak of that efficiency curve has a special name. It's called the best efficiency point, or BEP for short. This is the promised land for pump operation. It's that single, perfect flow rate where the pump is just in perfect harmony, converting the maximum amount of electricity into useful work. This chart shows you exactly why the BEP matters so much. Here, a great pump might turn, say, 85% of its power into useful work. That other 15%, it's just wasted as heat and vibration. And the further you stray from that BEP, the more of your money is just turning into useless noise and heat. So why does this matter? I mean, really? Because that wasted energy costs an absolute fortune. The difference between running a pump near its BEP versus way, way far from it can easily add up to tens of thousands of dollars in wasted electricity over the pump's lifetime. The bottom line is simple. Finding the BEP is finding the savings. Okay, so we know how to run the pump efficiently, but running it inefficiently, that generates extra heat and vibration, which can actually destroy it. And that brings us to our next section, how to keep the pump from tearing itself apart. This involves understanding two more curves, the power curve for motor sizing, and a crucial curve that helps us prevent a really destructive force called cavitation. Cavitation is every bit as bad as it sounds. One source I saw described it perfectly. It's like the pump is trying to move gravel. And that isn't just a sound. It's the noise of the pump literally tearing itself apart from the inside out. So how does this even happen? Well, it's a four-step chain reaction. First, the suction pressure inside the pump drops so low that the liquid literally starts to boil, even at room temperature, and it forms these tiny vapor bubbles. Then, as these bubbles get whipped into a higher pressure zone inside the pump, they collapse or implode violently. This collapse creates these tiny but incredibly powerful shock waves that just blast away at the pump's impeller, causing massive damage over time. To stop this, we just have to follow one golden rule. It involves two key terms, net positive suction head available, or NPSH-A, and required, or NPSH-R. Let's break that down. Just think of NPSH available as the pressure your system provides to the pump inlet. It's what you have. NPSH required is the minimum pressure the pump demands at its inlet to stop those destructive bubbles from ever forming in the first place. So, the rule is incredibly simple, right? The pressure your system has available must always be greater than the pressure the pump requires. As long as what you have is more than what the pump demands, you starve cavitation before it can even start, and you save your pump. It's that simple.
So, we've looked at all the curves that describe the pump itself. But here's the final critical piece of the puzzle. A pump doesn't operate in a vacuum, right? Its actual performance is determined by the system of pipes and valves and elbows that it's connected to.
This is where the system curve comes in. It's a completely separate curve that you have to calculate, and it represents the demands of your specific system. It shows you how much pressure is needed to fight against gravity and friction in your pipes at any given flow rate.
So how do we find out where the pump will actually operate? It's a simple case of supply meeting demand. There is only one single point where the pressure the pump can supply perfectly matches the pressure your system demands. That exact point of intersection, that's your true operating point.
This is the big aha moment. The pump curve showed us what's possible, but this intersection shows us reality. It tells you the exact flow rate, the exact pressure, and the exact efficiency you will actually get once that pump is up and running in your system. This is literally how you predict the future.
So, mastering these curves really transforms pump selection from guesswork into a science. But it leaves us with one last important thought. Real-world systems are never static, right? Valves open and close, filters get clogged, pipes get older, and every single time your system changes, that operating point moves. So the real question is your pump still on the right road, or has it been pushed into a zone of inefficiency and danger? Understanding this roadmap is the only way to know for sure.